I want you to do something for me. Go into your kitchen and make a cup of coffee. It does not matter if it's espresso or instant or the kind that comes out of a machine with 17 buttons. Just make a cup. Watch what happens when you stir in the cream. The white swirls into the brown. Slowly at first, then faster, until the whole thing is one uniform tan color. You cannot unstir it. You cannot put the cream back. You cannot reverse the process. And that seems obvious. That seems like it should be the most boring observation in the world. But that cup of coffee is hiding one of the most terrifying problems in all of physics. Because here's the thing. The laws of physics, at the deepest level we know them, are almost perfectly reversible. Run a film of a single electron bouncing off a proton, and then run the film backwards. Both films look exactly correct. Both films are allowed by the equations. Physics, down in the basement where the real rules live, does not much care about the difference between forward and backward in time. It's symmetric, it's balanced, it's clean. But your coffee does not run backwards, and the universe does not run backwards. And most disturbingly of all, the universe exists at all. And by the same equations that govern every particle accelerator we've ever built, every experiment we've ever run, by those equations, the universe should not exist at all. Not in a metaphysical sense, not in a philosophical sense, in a hard, precise, embarrassingly concrete mathematical sense, the universe should be empty. You should not be here. I should not be here. There should be nothing but a faint hiss of light in a dead, perfectly symmetric void. And the fact that you are sitting there right now, the fact that there is a chair beneath you and a planet beneath the chair and a star warming the sky, that is, from the perspective of the equations, an outrage, a glitch, an improbability so extreme it borders on the miraculous. And I want to tell you why. Let's go back to the very beginning. Not to the beginning of human history or the beginning of life on Earth. I mean the actual beginning, the Big Bang. About 13.8 billion years ago, in the first tiny fraction of a second after the Big Bang, the universe was unimaginably hot and dense. I'm not going to give you a temperature because the number would be so large it would be meaningless. Just imagine every atomic explosion that has ever occurred on Earth, all of them happening simultaneously in a space smaller than a proton. That's cold by comparison. That's what we're dealing with. At those temperatures, matter and energy are the same thing. Energy spontaneously converts into matter, constantly, everywhere. But here's the rule, the ironclad, experimentally verified rule. When energy converts into matter, it never, not once, not ever, produces matter alone. It produces matter and antimatter together in equal amounts always. One electron and one positron, one proton and one antiproton. Always pairs pair, always balanced pair, always equal. This is not a suggestion. This is not a tendency. This is a law. The law of conservation of charge, conservation of baryon number, conservation of lepton number. These laws demand perfect symmetry, equal matter, equal antimatter, always. Now, antimatter is real. This is not science fiction. We make it every day in particle accelerators. A positron is an electron with a positive charge. An antiproton is a proton with a negative charge. When antimatter meets matter, they annihilate each other completely, converting entirely into a flash of energy. Gamma rays, pure light, nothing left behind. So here's the problem. Here's the problem that should make you put down your coffee and stare at the ceiling for a while. If the Big Bang created equal amounts of matter and antimatter, then as the universe cooled and expanded, all of that matter and all of that antimatter should have found each other. Every proton with its antiproton partner, every electron with its positron, all of it, annihilating, leaving behind nothing but a universe full of light, a perfect, symmetric, utterly empty universe filled only with photons and no structure whatsoever. No galaxies, no stars, no planets, no chemistry, no biology, no coffee, no you. That is what the equations predict. And yet, here you are. I want you to feel how close to nothing we actually are, because this is not a small imbalance we're talking about. It's not like the matter won by a comfortable margin. Let me give you the number. In the first moments of the Big Bang, for every 1 billion antiprotons produced, There were 1,000,000,001 protons. That's the asymmetry. 1 part in a billion. 1,000,001 protons for every 1 billion antiprotons. Think about that ratio. If you filled a stadium with 1 billion people, and I told you that you needed to find the one person who was different, who was standing while everyone else was sitting, that's the scale of the imbalance we're talking about. And every single person in that stadium, all 1 billion of them, annihilated with their counterpart. Poof, gone, converted to light, except for one, that one person who was standing. That is what you are made of. That is what I am made of. That is what the earth is made of, and the sun, and everything you've ever seen or touched or thought about. We are the rounding error of the universe. We are the one extra proton, the remainder that could not find a dance partner. The universe did not create us. The universe tried very hard to erase us, almost perfectly succeeded, and left behind this tiny, embarrassing residue. And that residue is everything. Now I've told you the problem. The equations say perfect symmetry. The universe says imperfect symmetry, and something has to give. So the question physicists have been asking for 60 years is, where did the asymmetry come from? How did the protons outnumber the antiprotons, even by that tiny amount? What broke the symmetry? In 1967, a Soviet physicist named Andrei Sakharov was sitting in a prison camp. He was a dissident, a brilliant man punished for thinking clearly. And he was thinking about this problem, and he wrote down 3 conditions, 3 things that must all be true simultaneously for a universe like ours to exist. We call them the Sakharov conditions. The first condition, the universe must violate what's called baryon number conservation. In simple terms, there must be physical processes that can create more matter than antimatter. This had to happen. Otherwise, the numbers never get unequal in the first place. The second condition, the universe must violate what physicists call C-symmetry and CP symmetry. C-symmetry means that if you replace every particle with its antiparticle, the physics looks the same. CP symmetry means that if you replace every particle with its antiparticle and also mirror the entire system left to right, the physics looks the same. If either of these symmetries is perfect, then for every process that creates extra matter, there's an equal process creating extra antimatter, and you're back to square one. The symmetry must be broken. The third condition, there must be a period in the early universe when the system is out of thermal equilibrium. When things are perfectly in equilibrium, every process and its reverse happen at exactly the same rate. You need the system to be out of balance, running in one direction, before equilibrium is established. Now here's the beautiful and terrifying part. We have found CP violation. It's real. We first confirmed it experimentally in 1964 with kaons, particles that contain strange quarks, and James Cronin and Val Fitch won the Nobel Prize for it in 1980. We've since confirmed it in B mesons, in D mesons. The universe genuinely does treat matter and antimatter slightly differently. The symmetry is broken. It is a measured, reproducible, undeniable fact. But here's where physics becomes uncomfortable. The amount of CP violation we have measured is far too small to explain why you exist. By a lot. By something like 10 orders of magnitude. The broken symmetry we observe, as real as it is, produces only a tiny fraction of the matter-antimatter imbalance we need to explain the universe we see. It's like you're trying to explain why you're standing up, and I show you a ramp that could lift you 0.5 millimeter. The mechanism is real, the direction is right, but the scale is almost laughably inadequate. Something else is going on. There is CP violation we have not found yet. There is physics beyond the standard model that we have not cracked, and the universe, as usual, is not cooperating with our desire to understand it quickly. Here is a thought experiment I want you to try. Imagine you are the universe in the first microsecond after the Big Bang. You are hot, unimaginably hot, and you are producing particles constantly, matter and antimatter, spewing them out in pairs. And the rules say they should be equal. The rules have always said they should be equal. But there's a tiny flaw in the rules, just a small one. a slight preference, like a coin that is ever so slightly weighted, so that out of every billion flips, it comes up heads one extra time, one extra proton, one extra electron, one extra quark. And these tiny preferences are happening everywhere, in every cubic centimeter of the universe, billions and billions of times every microsecond. And those tiny asymmetries add up. And when the universe eventually cools enough that matter and antimatter start finding each other and annihilating, there is just barely more matter, 1 part in a billion more. And all the antimatter annihilates with most of the matter. And what's left over is us. Now ask yourself, how confident are you that that 1 in a billion preference was inevitable? How confident are you that those particular numbers, those particular constants, the particular way CP symmetry breaks in this universe, how sure are you that they could not have been slightly different, slightly more symmetric? And if they had been, there would be nothing here to ask the question. This is the part that keeps me up at night, if physicists are allowed to admit such things. The universe we live in is the result of a cosmic imperfection. Not a large imperfection, not an obvious one, a razor-thin, almost invisible departure from perfect symmetry. And without that imperfection, there is no structure. There are no atoms, there are no elements, there is no periodic table, no chemistry, no evolution, no history, no music, no science. There is just an infinite, quiet sea of photons, perfectly symmetric, perfectly featureless, forever. The universe, at its most fundamental level, appears to be balanced. It appears to be symmetric. The equations are beautiful, they're clean, they're elegant. And then reality shows up and says, not quite. There's a little wrinkle, a tiny preference, and that tiny preference is everything. That tiny imperfection is the difference between a universe of nothing and a universe of something, between emptiness and you. Some people find this disturbing. I find it exhilarating, because it says something profound about what kind of universe this is. It's not a universe that plays perfectly by its own rules. It's a universe that bends them just slightly in exactly the right places to allow complexity to exist, to allow structure, to allow you to be sitting there reading this and wondering about it. People often ask me if I believe in anything, and I always say the same thing. I believe in evidence. I believe in the equations. I believe in running an experiment 1,000 times and trusting the result. But when I look at this particular problem, when I look at the fact that we exist despite every symmetry in nature conspiring to prevent our existence, I feel something that's hard to put into words without sounding unscientific. So let me try to put it into physics instead. The universe did not have to be this way. The CP violation could have been 0. The Sakharov conditions could have all been met except one, and everything we are would have dissolved in the first second. The laws of physics we know and verify every day in every laboratory are the laws that by the thinnest imaginable margin allowed there to be something rather than nothing. And we are not the purpose of those laws. We are not the intended result. We are the overflow, the leftover, the 1 in a billion surplus that could not be canceled. And yet, here's the beautiful part. Here is the part that I think matters most. That surplus, that tiny, insignificant, accidental surplus, figured out how to build stars. It figured out how to make planets and oceans and cells and brains. That 1 extra proton per billion antiprotons became, over 13 billion years, the kind of thing that can ask where it came from. It became you, looking up at the night sky and wondering why there is something rather than nothing. And the answer is barely, almost not. By a margin you cannot adequately express in ordinary language. We exist by the narrowest margin the universe permitted, and that margin was enough. So the next time someone asks you whether the universe cares about you, you can tell them the truth. The universe does not care about you. The universe almost erased you before you started. But the equations had a flaw, a tiny, beautiful, inexplicable flaw. And you are that flaw. You are the imperfection in an otherwise perfect system. And that, I think, is a more interesting answer than being the center of everything. The equations say you should not exist. And yet here you are, absolutely refusing to cooperate. I find that admirable. Keep finding things out. See you in the next adventure.